And continue our discussions of nuclear energy, talking about fission in this video, and both in controlled fission with nuclear power plants and just a little bit on nuclear weapons. In a following video, we'll talk about 3 Mile Island, Chernobyl, and Fukushima. So fission. We've seen the binding energy per nucleon curve that has iron at the peak. Uranium is far to the right and down from that peak in terms of its binding energy per nucleon. When we have a large nucleus like uranium splits into fragments, we find that there's less mass after the fission than before the fission. So this fission energy release, when we have a large nucleus and the fragments, the main fragments are close to the peak of the binding energy per nucleon graph. Again, mass has been converted into energy in this process. So we'll be investigating that and some of the details with this as we take a look at this. So for the uranium, our main fragments are closer to the peak. We do have neutrons released that don't relate to this graph of binding energy per nucleon, but the main fragments are closer to the peak. We're releasing energy. Well, nuclear power plants, many of them are recognized by the large cooling towers, this sort of hyperbolic shape, cooling towers, and then a containment building that is rather large also. A cylinder with a dome on the top is one possible configuration. As this slide from OpenStax College Physics reports, electrical power is significant around the world coming from nuclear power plants, 16%. So how do we create fission in uranium? Well, it turns out uranium-235 is susceptible that when we add a neutron to it, it becomes unstable. You can kind of think of it vibrating back and forth, and as these particles get a little further apart, the amount of the strong nuclear force is decreasing because the distance is increasing. The repelling force from the protons is decreasing a little bit, but not as much as the strong nuclear force is decreasing. If you remember, the strong nuclear force is a short-range force. So this vibration, this kind of clumping together back and forth, left and right, goes too far, and we get two separate nuclei being produced. They have a surplus of neutrons, and not immediately, but eventually these isotopes release some neutrons as sort of a continuation of the fission process. In terms of uranium-235, again, a neutron comes in, it makes it uranium-236. That's unstable. It fissions. This particular illustration shows barium and krypton being released and two neutrons. If you take a look at the nucleon count, we still have to balance. So 139 plus 1 would be 140. 141 here. 141 plus 95 is the 236 that we started with. The one neutron here and the 236 nucleons in the uranium. But the mass is decreased. The total mass of these products is less than the mass of the neutron plus uranium-235, and about 200 million electron volts from one fission is released. Millions of electron volts. This nuclear process, much more energetic than a chemical process, burning coal or oil, that releases a few electron volts of energy in a chemical reaction per reaction. So we have much more energy being released here in the fission process per reaction. A chain reaction can occur because these neutrons that are released from the fission, they can be slowed down and then interact with other uranium-235 nuclei. And we're getting extra neutrons released in each step. If we have the targets available, then the number of fissions per second can increase. We control this for a nuclear power plant. It goes more or less uncontrolled for a nuclear bomb with a bigger release of energy in a short amount of time. So we need to investigate a little bit on how this goes. First, the nuclear bomb. This is not a detailed plan, but the basic outline is here. It takes a certain amount of mass to be a critical mass that will have a runaway chain reaction. So these subcritical masses, they have a larger surface area per volume, so there are neutrons that leak out and don't hit other targets. But if we make the two half spheres come together, merge them together into a spherical shape, now the neutrons that used to leak out of these flat sections of the hemisphere, now they hit a target, uranium-235 target in the other half sphere, and that can be a critical mass and lead to the explosion, the runaway chain reaction. Uranium ore out of the ground does not have enough uranium-235 to have this runaway reaction. It has to be refined, purified, and it's a whole involved process in enriching fuel up to weapons grade percentage of uranium-235 in the mix. Uranium-235 is a small percent abundance isotope in the uranium family, but it can be enriched in weapons grade. It's greatly enriched to give enough targets here. But this particular slide is just informing you that we have to have a certain mass in a certain shape to create a nuclear bomb. If we would have the same mass and it was in a pencil type shape, that would not be a critical mass situation. Too many neutrons would leak away without hitting a target to make the explosion. Of course, World War II was the motivation for creating nuclear weapons. It was reported that Germany was stockpiling uranium. There was a research program, the Manhattan Project, to build a nuclear bomb, and that was that program did accomplish that goal. And the nuclear weapon just releases a lot more energy in a short time than a chemical weapon. Makes a lot bigger pressure difference and destructive power in the explosion that takes place. So used twice on Japan, and again the wooden structures have been blown away. The structures with concrete can survive, the concrete can survive, but the high temperature, the high radiation, the pressure wave killed a lot of people. The more powerful bombs now are hydrogen bombs instead of bombs that use uranium or plutonium fission elements, but there can be a greater release of energy per pound when a hydrogen bomb explodes, and it combines a regular fission bomb, the uranium material, but then has hydrogen available to be fused together to give a big release of energy, much bigger release than what can happen for a bomb that just uses uranium or plutonium. But we're not going to go into those details. Instead, we'd like to talk about the first fission reactor, controlled fission. This is graphite here, and there's fission material inside this pile of graphite. There are control rods that absorb neutrons that can be pulled in or pushed out. The pushed in, pulled out. The timeline here is December 1942. Again, in the research done to understand fission to develop the bomb, experiments were performed on this fission material. And I think it was a little bit bold to put this first reactor in Chicago in a populated area rather than an unpopulated area, but the scientists were confident in their calculations that they could control the chain reaction, that it wouldn't run away, and it was successful. It no longer exists now, but this is a drawing. There was no photography allowed. It's a highly classified project, but they were doing experiments to verify that they could control the fission reaction. A nuclear power plant today, one particular design that we'll talk about here, the fuel rods are inside a special alloy. They're inserted into this pressure vessel. and then control rods are partially removed to allow neutrons to go across through the core and reach other uranium-235 targets so they can fission. The control rods have material that absorb neutrons and don't fission. Then there's also moderator material in here that slows down the fast neutrons that come out of a fission, that slows them down so they can be a source of future fissions. These slowed down neutrons work better than fast neutrons. But the moderator material is made of material that can have collisions with neutrons but is unlikely to absorb the neutron. So we get neutron happening from fission, hits the moderator material atom, bounces off, and we get it ready to engage in fission. So that's going to create an energy release in this core. This will be a steel containment vessel, several inches thick of high quality steel, sort of the first level of defense if a problem occurs, to keep the radioactive material in this vessel. That energy has to be removed or we would warm up too much. Q equals mc delta T we studied first semester. If we put energy into a system, the temperature will rise if we're not at a phase change point. So Q equals mc delta T, we're getting energy, Q, from the fission, and the water is then warmed up by these fuel rods. That warm water is extracted in this primary coolant loop. There are pumps that push the water through the regions in between the control rods and the fuel rods, pick up the energy and deliver it to a heat exchanger. And the heat exchanger produces steam in a secondary cooling loop. We have the primary cooling loop taking energy out of the core. We have a secondary cooling loop creating steam there and delivering that steam to turbines that then, by Faraday's law, will create electric current, will induce a current through the rotating coils and the magnetic field that's in the turbines. That's sent out by transformers out to our electrical grid. After the steam goes through the turbines, the steam condenses down to water, and pumps push this back through the heat exchanger again to form steam again. We have some emergency core cooling water available here, and it has in it material that absorbs neutrons. In case the control rods aren't doing a good enough job, this emergency water can be put in and absorb more neutrons. So the 3 Mile Island nuclear power plant looks like this. Big cooling towers. There are 2 nuclear reactors on the plant, and the Susquehanna River here in south central Pennsylvania was there to provide the cooling water that would then recirculate around the secondary loop. At least this is part of the condensation effect, having this cooling water available to the lake. So it's not uncommon for nuclear power plants to be built along a lake or a river or an ocean, in the case of Japan, and we'll talk about that. So those are the basics. That's just the basic introduction here for fission. The uranium fissions, it splits apart. There's less mass in what comes out of the fission reaction than what we start with. So energy is released. We can have chain reactions if those neutrons can be slowed down so they strike other uranium-235 nuclei, or maybe plutonium. There's a fissionable isotope of plutonium as well. And nuclear weapons, we don't control the rate of neutron production, and don't try to control the rate of fission, but try to get a big release of energy in a short amount of time. So I'm going to stop there. In the next videos, we'll talk about the 3 Mile Island accident and Chernobyl and Fukushima.